In the last video, we introduced the concept of a conditional probability. We saw that it gives a rational way of updating our probability measure based on given information. In particular, it defines a new probability measure on the sample space omega, which simply arises by restricting and renormalizing the original measure to the part of the sample space that is compatible with the information at hand. In today's video, we will cover the conditional expectation given that an event A has happened, also called the elementary conditional expectation. So, if we simply look at the terms involved, what could that conditional expectation be? If we recall for a second that the expectation of a random variable x is simply the probability weighted average of all the values x can take, then there's a natural candidate for what a conditional expectation should be. Since during conditioning we replace the underlying probability measure, the conditional expectation should be the same weighted average of all the values the random variable can take, just that we replace the original probabilities with the conditional ones. And on an abstract level, it's really as simple as that. For the ordinary expectation, we have a probability space omega AP, and we compute the expectation by integrating the random variable x with respect to the probability measure p. And for the conditional expectation, the only thing that changes is that we replace the probability measure p with the new conditional one, and everything else stays the same. But probably not everyone likes this abstract point of view, so here's an example. Assume that you roll 2 dice, and you are interested in the expected maximum of the values. To find this value, you first write down all possible outcomes of the sample space, that is, of rolling 2 dice. Then you assign probabilities to each of these outcomes, which in this case defines a discrete uniform distribution. Then you transform these values with your random variable x into the quantity you are really interested in, namely the maximum of the 2 dice. And then you push forward the probability mass onto these outcomes. Finally, you build your weighted average, which apparently gives a value of 161 over 36, which is about 4.47. So, now assume that you already rolled your first die and it shows a 4. How does this affect your calculations? According to our abstract recipe from before, the only thing we have to do is to replace the original probability measure with the conditional one. So we restrict the sample space to the area that is compatible with the information at hand, namely all pairs where the first die gave a 4, and then we normalize these values to have a probability measure again. After that, we can simply do the same things as before. We push forward the mass onto the image space of x. Then we build the weighted average of the values of x with respect to this new measure, and then we get that the conditional expectation of the maximum, given that the first value is already a 4, is apparently given by 27 over 6, which is 4.5, so slightly larger than before. So, just like the elementary conditional probability is really nothing special, the elementary conditional expectation is not a fundamentally new construction. It is simply the ordinary way of computing an expectation, just with respect to a different probability measure. Before we end the video, let's have a look at independence. Independence of two events A and B was characterized by the fact that conditioning on one of the two did not change the probability of observing the other. And for conditional expectation, this carries over immediately. If the random variable x is independent of the event A, the distribution of x is unchanged under conditioning on A, such that if we calculate the weighted average with respect to the conditional distribution, we end up with the same value as if we average with respect to the original distribution, simply because they are the same. So if x is independent of A, the conditional expectation is the same as the normal expectation. Okay, so that's it for the video. If you have any questions, comments, or feedback, let's discuss them in the comment section. Otherwise, thanks for watching.